All right, so we were talking about line integrals, right? And actually computing line integrals. We're going to go back into group work very quickly, but I wanted to explain this notation that I haven't. Oh, sorry. Let me. Sure. Yeah, this notation right here, I haven't mentioned, because sometimes you see this in a lot of like physics books and stuff. This one, this p dx plus q dy plus rdz. So, and then also just to set up what we were doing last time, just to remind ourselves what we were doing on Wednesday. So, right. Because we sort of said, okay, what we've got here is, so back to line integrals, back to, and I assume we were left really, but back to class. So if f, let's just say f is p, so this is some function, right? I mean, usually I'll write it shorthand as just, we'll just drop all the x, y, z's. But, and I think the book uses x, f1, f2, f3. The point is you have, you know, or if it's a two variable one, like, oh, I gotta stop the share. But if it's just two variable one like this, right? This is your p and this is your q. Right, I'm just thinking of it that way. P is 2x plus y, q is x. All right, I think I have you do some, I thought I had you do some, oh yeah, some 3D line integrals. So here's a 3D line integral, like that's p, that's q, that's r, right? So that's all I'm saying there. So if that's your expression here, and c is parameterized by r of t, which is, if you think about it, is like x of t, x is a function of t, y is a function of t, and z is a function of t, right? Then one way to think about r prime, well, r prime is really like x prime. So we could write that as dx dt I plus dy dt j plus dz dt k, right? When we do the like that. And then it's typical, it's kind of a goofy thing, but it's almost like if you think of these as fractions and you multiply through by dt, then r prime of t dt, it can be written as dx I plus, I'm going to put like equals in like quotation marks or something, plus dy j. This is kind of a notational thing. And then, so I'm just writing it kind of that way. But it's basically, I mean, this is a little tiny piece of the curve, right? That's kind of what we said. This is tangent. The dt makes it really short, so it's just basically a little tiny piece of the curve. And you can think of a little tiny piece of the curve made up with a little tiny x component, little tiny y component, little tiny z component. So this is just somewhat something notational. But then the integral f dot dr over c, like we said, is really the integral, I guess I should have said, t is between a and b. Or I don't know, sometimes I'll just keep writing c for now. So f of, we plug in the curve into the force, into the function, right? Dotted with r prime of t dt. But if we think about it, it's like dotting this with this, right? F dotting the f with the r prime. So if we dot these together, and also if I just write this maybe as pi plus qj plus rk, like that. Right, so if I dot these together, do you see what you get? You get pdx plus qdy plus rdz if you dot them. And so that's where that notation from the handout comes from. So that can be written as pdx plus qdy plus rdz. So this is notation. We dot product these. So this is really just a notation, because you don't really necessarily evaluate the integral this way. But it's sort of a classical notation. A lot of older books and stuff that you see, and a lot of the way, even we'll see the way like Green's theorem is stated, which is kind of the last big thing we do, is often stated in this form, using this form. So it's just a notational thing. Cool. Cool. Yeah, a lot of physics textbooks will use that also. So, okay, now let's get back to where we were. Back to where you once belong. Anybody watching that Beatles documentary? Anybody care about the Beatles? You guys are too young. Beatles are amazing. It's a Beatles documentary called Get Back on the, okay, Disney Plus. What? Yeah, it just came out at Thanksgiving. It's like 7 hours. I mean, I've only watched it like, it's like 3 parts in 7 hours. I've watched like the first 2 hours of it, but it's really good. Disney Plus. We all have Disney Plus, right? Gotta have our Marvel and Star Wars and Pixar fixes. No? How do you live without Marvel? I'll give you my password. Okay. I already gave like 5 friends in my whole family my password. Okay. So, anyways, yeah. So we were doing this, right? So let me just remind ourselves. I think of what. So we have this specific. So some computational examples, but there's something structurally interesting here, which is why I'm having you do all these. So we had F1, so this is just a 2D field. Those are all 3D. 2x plus y I plus xj, and F2, y and y minus x, yi plus y minus xj. And then we had 3 different paths from 0, 0 to 10, 10, right? We had a straight line path. That's 10, 10. This is C1. We had, well, the horizontal and vertical straight line path. So that's C2. When we think of this as 2 different, maybe C2A and C2B. And then there's this parabolic path. If you look at the handout following y equals 1/10 x squared. So that's C3, something like that. And C1, we said, was just x equals t, y equals t from 0 to 10. Or you could do x is 10t, y is 10t from 0 to 1. C2, well, the first part of the path, I think you guys did this, was t and 0, right? And the second part of the path was 10 and t. But you just set this up as 2 separate things. I mean, you can try to force this to be 0 to 20 and have the 0 to 10 be this and the 10 to 20 be that, but you don't need to do that. You're gonna have to break it up anyways. And then the third path is not, I don't think any of the groups really got, or maybe one group got to this, which like, basically x is t and then y is 1/10 x squared, so y is 1/10 t squared, right? So x is t, y is 1/10 t squared. It's also from 0 to 10. Okay, so these are the paths, these are the two fields. And then I wanted you to compute all 6 of these different, sorry, if you're watching on Zoom and that went off screen, just make sure you're looking at the handout also. Yeah, so then just to think what we're doing here, I want to collect some data, which is I want us to compute a bunch of different ones and see. I think there's an interesting pattern which you may have already noticed a little bit with F1. Okay, just wrote all that as fast. Okay, so we did the integral of a C1, F1, the integral over C2, and the integral over C3 along C3, F1.dr. And so you guys already computed both of these and you found 200, right? So I want us just to compute all of these. Then the integral over C2, I don't think anyone's done, I'm sorry, integral over C1 of F2. So the second vector field. Okay, so basically I just want us to see what's going on here. Like I just want to answer all these because I think there's something interesting. Sort of cryptic because I want you to see it for yourself. But yeah, so I want you guys to finish filling out this table. You guys have done the first 2. So that's basically what all of these say. And then there's this stuff, if you finish that, you can start looking at the stuff about gradient fields on the second page of the handout. But it's basically what problems 1, oh, let me share screen here. It's basically what problems 1 through 4 on the handout are about, are just like computing all of these. Okay, and then there's this stuff about gradient fields you can get to later. So let's go back into groups, do that. And then maybe we'll come back towards the end of class and talk about some of this gradient field stuff. But you can pull the handout up also, since it's like a 3-page handout. So if we're gonna go through all this. I mean, a lot of this will go into next week, but you can pull the handout up on your iPad or whatever and start working through that. So, okay, let's do it. Group work, woo, yes. Yes, group work, exciting. I'm gonna pause the recording. Okay. So maybe we'll come back together. I'll let you guys talk it out for another minute. Okay. I erased the fields, didn't I? What are the fields again? X plus y, x, y, y minus x. Share everything. Oh, damn it. Okay, maybe that's good. Sorry, oh, I didn't mean to interrupt you. Let's come back together just for a few minutes. I want to kind of say something here. So this is the field. This is the F1 field, the 2x plus y comma x. Guys, everyone, hello. And this doesn't wait, actually, let's see. It doesn't compute line integrals directly, this little applet, but it will compute circulation, which is, you know, an integral around a closed loop. So what is an integral around a closed loop? So for example, this F1, if you went like out the straight line path and then came back down and over, what do you think the total integral would? That would be a closed loop, right? What do you think the total integral would be? This was 200, right? And then you go this one backwards. Yeah, if you go backwards, it's actually negative. If you trace the path backwards, you actually get negative of what you got. So 200 minus 200, you get 0. And in fact, yeah, if it's path independent and I start and end at the same point, well, what's the dumbest curve that starts and ends at the same point? That's a dumb curve. That's a very sophisticated curve to me. What's the dumbest curve that starts and ends at the same point? The point. You don't go anywhere. I guess I should said like path that starts and ends at the same point. You just stop. You just stand there. So what's the line integral if you don't move? 0. So in fact, the integral around for a path independent field, the integral around any closed loop should be 0. And if you look here at the bottom left of the screen there, it says circulation 0. Doesn't matter what. This will just do these rectangles for you, right? So that's interesting. But if I switch this to the y minus x, comma, oh no, y comma y minus x, sorry. Y minus, oops. If I do that field instead, well, here now, I get different values of the circulation, right? Oops. Depending on where I start. And so I get non-zero, which means if I went one, like if you think about, you can think about this, like if I have a rectangle like this, I could think of the path from here to here, but two different paths. One would go this way, and then it would go like that way or something, right? And so you get different answers. So another term for this, besides path independent conservative, can also say, another term is circulation free. These are all synonyms for each other, which we'll see. I mean, we'll sort of talk about this a little more systematically on Monday, but that's the first thing that's kind of neat. The second thing, let me just go back to the board maybe. So, yeah, well, actually, well, okay, yeah, let me just go back to the board for now. But so the thing that was on sort of page 2, I don't going to end up on the screen. The thing that was on sort of page 2 of the handout was this thing about gradient fields and potential functions. So here it turns out that if we look at the function x squared plus xy, was that it? Then the partial x, well, the gradient of f, right, is you take the partial x, which is 2x plus y, I plus the partial y, that goes away and you get just x. It's j. That equals f1. So in fact, yeah, this is actually a field. F1 actually arises as the gradient of some function. The vector field arises as the gradient of some function. I guess really there's a fourth term for this, which is gradient field. Sorry, there's so many different. Just all these different things that turn out to kind of be equivalent. Path independent conservative is just a terminology. Circulation free means the integral along closed loops is 0, which is sort of clearly independent, clearly equivalent to path independent, and then a gradient field. So this is a gradient field. This, it turns out, the second one is not. We'll talk in general about if you're given a field, how to construct the, oh, this is called, yeah, so F1 is gradient field, and the function is called its potential function. So this is like when potential energy and stuff comes into play. This is what's going on there. So, but really what it is like, it's almost like, what I want to say is that F1 is like the derivative of little f. The vector field is the derivative of, because that's kind of, it's all the information. We have the two partial derivatives. So it's come together, they kind of make the derivative. The gradient in some sense really should be the derivative. And so little f is kind of like an antiderivative of F1. You can check, let me just kind of, I'll come back to that in a second. You can check this as not, because if F2 is the gradient of some function g, then that would mean the partial x would be that y, and the partial y would be that y minus x right there, right? And you can try to sort of, well, there's a way to sort of partially anti-differentiate and see that you don't get something compatible. But a better thing to do is actually to differentiate both of these. Take the partial y of this and the partial x of that, because the mixed partials are the same. So here, g sub xy would be 1, right? Because if I do the partial y of that. But g sub yx is supposed to be equal, but the x derivative of that is -1. And that's bad. I can't have 1 equals -1. So this is not a gradient field. Okay, but just the last thing I want to do before we run out of time, let me just say this, because this is kind of cool, I think. Stop the share, didn't I? Yeah. Let me just say something. So I said, like, we can think of F1 as the F1 up there as the vector field as a derivative. Think of, this as the derivative of f of little f. Think of little f as antiderivative of big F1. When we integrate from 0, 0 to 10, 10, how do you normally integrate in, if you have a function and you know it's antiderivative, how do you integrate it? Back in single variable calculus. What's the whole thing? How do I integrate 2x? Yeah, you do the antiderivative and you plug in the bounds and subtract. So the antiderivative, does this equal little f from 0, 0 to 10, 10? That would be the analog, right? The analog of the fundamental theorem of calculus. Analog of fundamental theorem of calculus, FTC. Well, the function is x squared plus xy, right? So x squared plus xy from 0, 0 to 10, 10 is 200 minus 0 equals 200. And so actually, there's this amazing way to integrate that it's like, you don't actually have to compute the line integral directly. You don't have to parameterize and plug in and everything. You can actually just plug in the endpoints and find the potential function, which is like the antiderivative, plug in the endpoints and subtract. So that's kind of the cool. There's an analog of the fundamental theorem of calculus called the fundamental theorem of line integrals, which is basically right there. So cool. All right. So I just blew all your minds, I know. try to recover over the weekend. And we'll talk about this a little more systematically on Monday. Thank you guys. Please straighten the chairs and erase the boards. And problem sets due at 5. I'm also downstairs in room 113 as usual, like at 11:40 with my, supposedly for my Math 250 class, but it's just office hours. So you can find me there too. If you can find me now, right, the next hour after class, you can find me. It's 113 from 11:40 to 1. And maybe in my office at 2:30. All right, take care, guys. Thank you. I'm gonna stop the recording.